David Bader will be presenting. He is a distinguished professor in the Department of Computer Science and founder of the Department of Data Science and inaugural director of the Institute for Data Science at the New Jersey Institute of Technology. His interests are at the intersection of high-performance computing and real-world applications, including cybersecurity, massive-scale analytics, and computational genomics. David Bader is a fellow of the IEEE, AAAS, and SCIEM. Please welcome David Bader.
Thank you, Bill. Thank you, Bill, for that introduction. Wow, what a long, strange trip it's been. So I want to thank the IEEE Computer Society for awarding me the Sidney Fernbach Award, and also for the organizers of SC21 for inviting me to give this talk this morning. And my talk is entitled Innovations Solving Global Grand Challenges. And what I want to do is tell you about some of the innovations that led to my building the first Linux supercomputer and also pioneering scalable combinatoric algorithms specifically for graph analytics and other techniques. Now, this award is named for Dr. Sidney Fernbach, who was born in 1917 in Philadelphia and passed away in 1991. And the award was named in his honor and his memory in 1992. He, as I mentioned, was a first-generation American. His parents were immigrants. And he went to school at Temple, at Berkeley for a PhD, and then worked at Lawrence Livermore National Laboratory, where he was head of the computation division, later the theoretical division, and was really the pioneer for putting high-performance computing to use for solving science problems, for instance, the physics problems that he was working on. So we really owe him a great deal of credit. So he and I are both essentially first-generation Jewish Americans born in Pennsylvania. We have something similar there. And to tell you about his family, I'd like to understand where he came from and put it into context. His father, Shmuel, was born in Galicia, which is now modern-day Eastern Europe, and immigrated to the United States in 1907, and he worked in Philadelphia as a furniture upholsterer. His mother, Berta, also was from Kolomaya in Galicia, Eastern Europe, and she immigrated in 1909. And this is very similar to my own family history. My grandfather, Louis Bader, was from Rupčica, Galicia, and the same region, who first went to London and then emigrated to the United States in 1912, and he worked as a hat maker in Manhattan. So here's his World War II draft registration. You'll notice here that he was working at Newland Hatware at 22nd West 4th Street in Manhattan. So just a trivia question, maybe if you're using the chat at the end of the talk, you can try to guess what research institute now stands at that same physical location. Now, my mother was born in Vienna, Austria, and World War II had broken out, and there was a lot of Nazi persecution of Jews, and she was placed on a rescue operation called the Movement for the Care of Children from Germany, or better known as the Kindertransport. This is a picture of her shortly before she left Vienna, and this is the line from the record of her exodus. I talked with her yesterday. She is 87. She was sorry she couldn't be here, but she's a lot happier today than she looks in this picture. And eventually, she was able to come to the United States. My grandfather, Isaac Rosenbaum, was taken during a Jewish attack called Kristallnacht in Austria in November 1938, and he was jailed in a concentration camp, Dachau, from 1938 to 1939. And over here is a postcard, just a sample of one that he was able to send to my grandmother on concentration camp stationery. And this really affected my upbringing and my life. In 1990, I was taking a class as a student, and I read an essay by Edgar Kupfer Koberwitz, who was also jailed in that same concentration camp, Dachau. And it really motivated me to think about my life and how to impact the world by really practicing peace. And for those who know me, I've been a vegan for over 30 years. I'm wearing my vegan suit and vegan shoes and vegan tie. So you're all familiar with this. But it really was this turning point, this moment in 1990, that I dedicated my life to solving these real-world problems that really make a difference to populations. And so in my talk this morning, I've arranged the talk into 6 segments about different pioneering innovations that really need to come together to solve real-world challenges. And I picture that in the center of this diagram. And going around, I have applications that really enable users, innovations in architecture that are really building the new hardware solutions, people, because we have to engage with new faces of computing, education, which is really establishing new academic disciplines that are needed to solve these problems, software for developing new programming methodologies, performance to really get the most performance out of hardware, software, and doing the co-design. And the talk will go through each one of these areas. But as I mentioned earlier, the main contribution for this award was my designing and building of the first Linux supercomputer. And this has had tremendous impact. In fact, today's #1 supercomputer, Fugaku, that Satoshi Matsuoka, my colleague at Riken in Japan, runs, really exhibits the performance and the capabilities that were made possible by this contribution for this award. So let me start by talking about applications, and I put applications first because at the end of the day, what we want to do is solve real problems, and the applications must drive everything else. So I keep my eye on the applications, and just to give you a little bit of a thumbnail or some brief slides on some work that I've done, I was very early in looking at algorithms and computing techniques that were going to be needed to reconstruct the tree of life of all of the organisms and life on the planet that's estimated to be from 10 to 100 million organisms. So I worked on an NSF-funded project called Cypress that led to algorithms and code like Grappa that have been instrumental for doing this research and really used that Linux supercomputer that I talked about earlier. I've also worked on NIH-supported research on reconstructing and predicting secondary structures of RNA. And this is a very important problem as we're trying to understand viruses such as influenza, HIV, and others, for instance, the current pandemic that we're in, and being able to quickly fold these types of molecules is a very important and also a very highly computational problem. I've worked on graph algorithms, and we see graph algorithms everywhere from our power distribution networks, and we know electricity is important for everything from our food supply, transportation, communication, heating and cooling, etc., from understanding massive social networks, for doing routing in ground transportation, understanding congestion in urban environments, or evacuating populations during emergency events, all the way to looking at problems from biology and genomics. These are some of the types of real-world problems that are enabled by graph analytics. And also problems in surveillance and intelligence. For instance, certain activities are often suspicious, not because of the characteristics of a single actor, but because of the interactions among a group of actors. And we can model these interactions through graph abstractions where the vertices are entities in the graph, and their interactions are directed edges that we place in the graph. So on the left is a diagram of a template matching problem, or better known as subgraph isomorphism, for looking for a pattern within raw data. And on the right is a graph of individuals. This is potentially a terrorist network where you may be trying to find the most influential actors in these networks. So these are also very important classes of graph algorithms. But also we can apply these social network algorithms to having more resiliency on the electric power grid, or even applying it to problems in public health. For instance, I worked with Kamesh Maduri on a cancer genomics problem of understanding the human proteome and trying to identify proteins that would be like finding a needle in a haystack for the ones that have been implicated in disease and cancer. I also led the first study of all of the public tweets streaming into a supercomputer and building a graph out of the follower and followee network and looking for influencers in that network during breaking events. For instance, I have some ad hoc results on a previous pandemic, H1N1, an influenza virus that we thought would have double-digit mortality around the globe. This was fall of 2009. And again, being able to analyze the full public tweets in real time was quite a remarkable event. And in our results, we were able to pick out commercial news sources, and also we were able to pick out the US Centers for Disease Control and Prevention, government agencies, but we were also able to pick out very important influential handles that you would never think of tuning into during a breaking event. So let me get to my next area of innovation, and this is in people engaging the new faces of computing. And I really want to thank my mentors that I've had in my career, both early and even currently. I talk with my mentors as frequently as I can, and I encourage all of you to think about who are your mentors, who can you learn from, who can you network with, and who can you go to when you're thinking about solving problems and you want to get really a big perspective on what the next step should be. So I want to recognize just a set of my mentors on this slide, but also those who have worked in my research group, from postdocs that I've had like Tanya Berger-Wolf and Tiffany Williams, Henning Meyer-Henke, and Yuzhang Sun, and also my current research group with my research scientist, Dr. Zihui Du, and my current PhD students, Fuhan Li and Oliver Alvarado Rodriguez, who are doing some incredible research, as well as the alumni from my group, my PhD students who have really done fantastic work and gone on to do even better things in their careers. I want to dedicate the talk, though, to my father, Morris Bader. Here he is pictured in the 1970s. He was a chemistry professor, and here he is at his office. True to form, he's wearing suspenders in both of these pictures. He was typically reading something. He passed away a number of years ago, and the inset picture is him about a year and a half before he passed away, reading to my child a book. And he was really an out-of-the-box type of guy. But being in chemistry, he really wanted to understand computers, and in 1965 went to IBM TJ Watson, and he learned a new programming language, Fortran, and then later RAT4. And just my whole childhood was all about Fortran and RAT4. In fact, here's a picture of us in the 1970s, 1972, and here he is at the top, a PhD in chemical thermodynamics, and very early into using computers and writing numerical algorithms, and even created a business selling scientific software. My mother has a master's in biochemistry. My brother William, a master's in computer science. My brother Joel, a PhD in theoretic chemistry. Here I am, PhD computer engineering, and my twin sister Deborah, PhD in molecular biology. And if this wasn't enough letters in our family, she decided to get a DVM or a vet degree as well. So here we are, and this was my upbringing. You see everyone mostly getting along in this picture. But a few years after this picture was taken, I got my first job. My dad paid me a penny punch card to take a program that he had from his IBM 1030 and enter it into a brand new mainframe that he had at Moravian College, a DEC PDP 1145. So this was my first computer, and I connected to it from home using this ADM3A terminal and this 300 baud modem. And actually, that was a fast upgrade from our 110 baud modem before that. And I would type in these programs. Probably before I could read and write, I was putting in these cards and learning how to program this PDP 1145. And this really got my thinking about hardware. I liked having a computer at home, and I always wanted to be able to do some interesting things and soon thereafter learned about parallel computing, and I really wanted a parallel computer of my own. So in the late 80s, I was interconnecting personal computers that were the commodity technology. In the early 1990s, operating systems became commodity, and also networks, and I was putting those into systems. And then by the mid-1990s, high-performance nodes were available, and I could interconnect them with high-speed networks. And then by the late 1990s, I could integrate also open-source job schedulers, commercial compilers, and high-speed interconnects that really led to the first Linux supercomputer. But it was the notion that we could take commodity, commercial off-the-shelf technologies and use them in high-performance computing. What I recognized early on were the economics were changing, that to build high-speed and high-performance computers, we would have to necessarily leverage these commodity technologies, and they would displace traditional supercomputers. When I was an undergrad, a buddy and I discovered a closet full of Commodore Amiga 1000s that were donated to our university, and they were just collecting dust. So we decided to build a parallel computer, and we connected them together in a network, and we were very excited by that. So maybe one of the very early clusters of personal computers. In 1993, I was really excited because the Unix distribution of FreeBSD, the first version, was made available. It was openly available in fall of '93, and I decided that I wanted to build a cluster with this FreeBSD distribution. And at the same time, we were using parallel machines that had their own message passing structures, their own proprietary message passing, and the MPI, message passing interface standard, was emerging, and also implementations of it like MPitch. And I thought if we put these together, we could have supercomputers at home, and that was what really drove me. By 1996, I had integrated a cluster of DEC alpha servers. Each one of them had 4 alpha processors inside of them, and connected them through a DEC GigaSwitch ATM. And I had to build my own messaging layer. I had to figure out how to program it, and I'll tell you more about that later, because this was a hybrid machine with multi-core nodes and a network between them, where just running MPI between them wouldn't give us the full potential of the architecture. In 1998, I had joined University of New Mexico and decided to build my first Linux computer. The machine on the left is the first Linux supercluster or supercomputer, and I integrated into this machine 16 Intel Pentium 2 processors running at 333 megahertz and a Mirrornet switch, and was able to put on a job scheduler, an open source job scheduler PBS that NASA was using. I was able to use both freely available compilers from GCC and also commercial compilers from the Portland group to get higher performance, and put this machine on the Globus grid, and really showed off the potential of having a commercial off-the-shelf supercomputer. And I took this idea to Larry Smarr at NCSA, the founding director of NCSA, and I made a pitch that this really is the future of supercomputing. Through the support of Larry, the Alliance, and the National Science Foundation, we acquired $400,000, and I was able to build and construct the machine on the right, Roadrunner, that was the first Linux supercomputer that was placed on the national technology grid and made accessible to the broad science community. So let me have you listen to Larry tell about this story.
One of the most significant events that occurred in this period was when David at University of New Mexico, as a member of the Alliance, created the first commercial off-the-shelf supercomputer. In other words, a supercomputer built of PC server technologies, and he put it on the national technology grid. So here was a commodity-built PC-based endpoint going into the national technology grid. And I actually, as director of the Alliance, was invited to come down and help turn it on, along with Senator Domenici and the president of UNM. This, as we will see, is a historic event. And it took resources from the Alliance, but it took David's creative energies and innovation to do that. Significantly, this year at Supercomputing, David will be awarded the Sidney Fernbach Award, which is effectively the largest, most important award given out at Supercomputing and by the IEEE Computer Society. But I think, David, I'm going to show how this effort of yours has enormous historic resonance. Because here's from the article in the Communications of the ACM in '97. But I want to just say to you, David, that it was your vision that you could build a commodity off-the-shelf component, put it as an endpoint on the national technology grid, that really was the original idea, I think, that led straight from back in 1997 up till now.
Thank you, Larry. And the notion of having Linux supercomputing took off like wildfire. By 2004, half the machines on the top 500 list were running Linux. By 2010, 90% of the machines. And by 2018, every machine on the top 500 list was running Linux. So this is quite a remarkable event that has really stood the test of time as we see this, the dominant approach in supercomputing today. Now, to get the DEC system that I showed earlier working, I had a challenge of having hybrid multi-core, multiprocessor nodes and a network between them. In the late 90s, I came up with the first programming methodology for hybrid use of message passing and multi-core, where we optimized for the shared memory on the node and message passing between the nodes. And this is one of the dominant programming methodologies of systems today. The next innovation is education. And it's quite important to look at how we train students and how we educate our community. In 2005, I founded computational science and engineering at Georgia Institute of Technology and created master's and PhD programs that have been highly successful in training students for working in these areas. We launched an online master's of analytics, and I built the school into the top research school at Georgia Tech during my 5 years as the school chair. In 2009, I moved to the New Jersey Institute of Technology, where I am the inaugural director of the Institute for Data Science. And this semester, I founded the Department of Data Science. I created the Bachelor's in Data Science that launched now. And we have a planned launch of a new PhD in Data Science that will occur next fall. Now, it's not often that once in your career you create a new discipline, let alone twice. But I found it very important to create new academic disciplines as homes for our researchers and new academic programs to really train the next workforce, to look at areas that fall at the interface between traditional disciplines and look at the right curriculum and the right research strategies to really have an impact for solving real-world problems. I've been very fortunate to work with a number of companies on this slide, as well as organizations, foundations, and government agencies. And this has provided a path for translating the research from our basic research at universities to going into labs and production at a number of companies, national labs, and agencies. So I thank everyone for all of that support. The next area of innovation that I want to talk about is in performance. And as many of you have known, I've been a proponent of accelerator technologies. which shouldn't be a surprise because accelerators often come from other areas of commercial off-the-shelf technology and other commodities. For instance, gaming and entertainment has been a huge sector, and Sony, Toshiba, and IBM built the IBM Cell Broadband Engine processor that was in the Sony PlayStation 3, and I helped repurpose this processor by directing the first Sony, Toshiba, IBM Center of Competence for the Cell BE processor, and using this in to accelerate a computing system that became the architecture in Roadrunner, the first petaflop supercomputer at Los Alamos. I also worked very closely with NVIDIA throughout my career. I was a lead scientist in their DARPA Ubiquitous High Performance Computing, or UHPC, program project called Echelon for extreme scale compute hierarchies with efficient locality optimized nodes. And this is the project that really has given you the high performance GPUs that we see today and has accelerated such a large percentage of the machines on the top 500 list. So these are the hallmarks of accelerators, of taking this technology and integrating it with our high-performance computers. As was mentioned earlier in the talk, I've also innovated in areas of hardware-software co-design for graph analytics. Victor Prasanna and I were co-PIs in a DARPA Hive award for building out graph technologies on the Hive chip that Intel is moving forward with. And this work has really also been recognized as part of the Fernbach Award, as I've had many firsts in scalable algorithm design and implementation. For instance, in single source shortest path algorithms, creating the first parallel between a centrality algorithm, an approximate between a centrality algorithm, winning the 10th DIMEX challenge, mixed challenge for community detection, streaming community maintenance algorithms, as well as many of the best performing graph algorithms for GPUs. I like to think of my work in data science and graph analytics in terms of this quad, where I have 4 quadrants split apart by these 2 axes. On the x-axis, I have objects, from known objects on the left to unknown objects on the right, and I have patterns on the y-axis, from known patterns on the bottom to unknown patterns at top. The lower left-hand quadrant, where we have known objects and known patterns, is where traditional relational databases work very well with schemas to be able to query data sets. On the upper left, where I have known objects but unknown patterns, a scenario may be an organization that has an insider threat who keeps tripping up some security tripwires, and a security officer notices it and wants to investigate what is that individual up to. Or on the lower right, I use this example of having a template that I'm trying to find within a larger set of observed data, so a known pattern and unknown objects where I may be doing subgraph isomorphism to detect it. But where I'm really focused in my research is discovery, this unknown unknowns, or this upper right quadrant, where I have data that I can't learn from because I don't know what's in there. I don't know if there are any patterns, anything I can find. I can't do machine learning on it because I don't know what to learn. So I try to build relationships in that data, and I build those relationships into very large graphs. And by performing massive scale graph analytics, I'm trying to reduce surprise in application areas by leveraging this 4th quadrant. This is moving data science from what I have on the left of the slide, where classic high-performance computing and supercomputers do extremely well, where I can take data sets, load them into a supercomputer, and ask queries of them. This is really good after something egregious has happened and I want to take my logs and load it in and ask a question. So I think of this as reporting the news. Where I want to get to is predictive analytics, where I'm looking at data as it's generated from sensors on the fly, and I want to anticipate the future. And that really requires building specialized analytics and data structures for these rapidly changing data sets with very low data reuse. And I have to focus on memory operations rather than floating point operations per second. So this has been the hallmark of my research. I built out a framework called Stinger for spatiotemporal networks and graphs, one of the first streaming graph frameworks that existed. And I built this out to really tackle emerging real-world problems, including detecting community structure in large social networks, or defending the nation against cyber attacks and giving attribution to those attacks, discovering insider threats within large organizations, improving the resilience of the electric power grid, and even detecting and preventing disease in human populations. These applications are very, very challenging because of the sparsity and lack of locality in the massive data, and also the design of parallel algorithms for these massive streaming data analytics. So we need to design new exascale supercomputers that are energy efficient, resilient, and easy to program for these tasks. Today, I'm proud to be supported by a National Science Foundation project called High Performance Algorithms for Interactive Data Science at Scale. What we're doing is democratizing supercomputing. We're leveraging an open source big data framework called Arcuda that was initially developed by the Department of Defense. And what we're doing is building out graph analytics into Arcuda. The illusion is that a data scientist can use Python, which is the lingua franca of data scientists, and very productively write their analytics. But on the back end, they're able to use Chapel, a HP Cray high-performance compiler that can run on everything from a laptop to a supercomputer, and is really doing the heavy lifting of the data movements. This framework is all open source, and we already see use cases and users that allow the rapid implementation of data science problems in graph analytics that would overwhelm a laptop, but with the same ease of use can run on these back-end supercomputers. When I think about high-performance computing and supercomputing, I created the first Linux supercomputer by leveraging COTS, commercial off-the-shelf technology. We're seeing the two swim lanes of high-performance computing and data science coming together in the future of exascale systems. We clearly see that machine learning and AI have had a tremendous impact. We're already leveraging commodity mobile technologies. For instance, the ARM chip, which powers Fugaku, the #1 top supercomputer in the world, leverages ARM. And that we're going to see a lot more of in exascale systems, I predict. From gaming and entertainment, I told you about accelerators like the cell processor, and also GPUs that are now powering about 90% of the machines on the top 500 list. We're using these accelerators to get high performance. And again, we're repurposing a technology that's been developed primarily for gaming and entertainment, and figuring out how to rework it and reuse it to do science and technical computing to our advantage. But some other areas that I think we're going to see in the future being leveraged for exascale systems. One comes out of the sector of personalized health. I'm wearing my health fitness device on my wrist over here, and I know we have sensors everywhere with the Internet of Things and new products. This reliance on sensors and being able to gather data off of sensors running efficiently on low battery power, I think we're going to see those technologies integrated directly with supercomputers. Also, with the machine learning and AI boom, we see a lot of custom accelerators, custom silicon, custom chips and systems, and those are going to be integrated as well naturally into our exascale systems to do both machine learning and AI, but also implement algorithms that we haven't even thought about yet. So I think those accelerators are going to be quite important. Also, banking and privacy is changing. We see blockchain technologies and new security emerging, and this is going to lead to new custom ASICs and new technologies that I think we're also going to leverage within the exascale systems of the future. And finally, data centers are fundamentally changing. We're seeing the ability to co-locate data sets together to do processing within the memory subsystems and within the data frameworks and new data appliances, really leading to something that I coined here first as super memory technologies. And we're going to see those integrated as well into our future exascale systems. And remember, it's the applications that must drive all of this. And those applications are global grand challenges that we need to solve. And so it's for us to really implement the algorithms, the software, hardware, to educate students and our next workforce to be able to use these together and design new algorithms to really improve real-world problems that matter to our populations. So I used these 6 areas of innovation that I went through in applications, architecture, people, education, software, and performance. And to really summarize this Fernbach talk, my final thoughts are that the innovation really occurs at the interface between traditional disciplines. In order to solve these problems, I've had to go through a number of these 6 areas to solve problems. I wasn't satisfied with the status quo of fitting within one silo or one discipline and spending my career there. I really looked at how to broadly impact the future, which is necessary to solve the problems that are meaningful to our population, to keep us safe, to keep people fed, to keep our countries safe, to keep everyone happy. This is the world that we live in, and we have many problems facing the world, from conflicts around the world to the climate crisis and other areas that we just can't wait. We need to understand health. We need to understand severe weather events. And these are the problems that we should be working on. And finally, be a Fernbach problem solver. No matter if your roots are in furniture upholstery, like Dr. Fernbach's, or hat making, like me, I encourage you to really think about the problems and what you can do to fill those gaps and really have innovations in your own careers. So I want to thank you for your attention. I appreciate the Computer Society and the 2021 Sidney Fernbach Award, and thank you again for your attention.
Thank you. Again, let me remind you to use the QR code to access the Slido system for the questions. I'll start with a few that have already shown up. You covered a lot of ground in many different applications. A number of the questions are asking about specific ones. First one here is, how much does resilience on the power grid help the nation as a whole?
So how does resilience on the power grid help the nation? We've already heard about blackouts that affected San Diego, New York City, and even Texas, but this is a problem that affects life and limb. Whenever there's a power outage, we have no heating and cooling, people die. And so we may lose our applications on our phone, we may lose communications, but we really also lose basic life necessity. The power grid is built off of some old technologies, and what we're trying to do with understanding resiliency of the grid is to figure out how to basically shore up the system. And so I think it's a very important problem to work on, and will continue to be a problem because, as I mentioned, everything from our food supply, communication, transportation, and now everything that we rely on really requires electricity everywhere at every time.
Another different question, given your experience founding departments, how much does department title affect foundational educational topics and goals? And how much overlap is there in basic skills between the 2 departments you founded?
So department titles, what's in a name? At the time I founded Computational Science and Engineering, it was really the notion of how do we produce students that would be able to do research in this community at supercomputing and working for our national labs and really engaging with the broad science and engineering area. at the time, computer scientists typically looked inward and worked on problems of architecture, networks theory, etc., but often did not look that closely at the applications. And what I tried to build was a community of collaborative computer scientists who would work with the physicists, chemists, the engineers, those in finance, to problem solve, to be experts at working on real problems and innovating in both that discipline area, but also innovating in computing. In data science, we see an explosion of need for data scientists. It's probably one of the most sought after majors today. I see a lot of synergies between computational science and engineering and data science. As we start to collect more data sets and massive data sets, we need high-performance computers to analyze those. Look at the Arcuda framework that is purpose-built to handle tens of terabytes of data sets that would overload what we could do on a laptop. And the performance requirements of making decisions with data in near real time really requires the same technologies and the same innovations that we have in the high-performance computing and supercomputing world. So hopefully I've addressed that question, but I'm really excited by these disciplines. And I think about data science also more broadly than just machine learning. Data science includes the systems that we're using, the architectures, the hardware, software, co-design, as well as the algorithms and the applications.
So another question. Ethics is a hot topic this SC, including this year's plenary. How do you manage your peace-first mindset in an increasingly complex HPC landscape?
So the question is about ethics and peace, and I really think about that in everything that I do. When I address a problem, I'm often thinking about what is it that's going to keep people safe. My own family history is that I lost much of my family who were killed in World War II and the Holocaust. And it was having a country to come to like the United States and to really be a patriotic citizen of my country and to think about building bonds with those around the world. Many of my students are international and I travel and have really engaged with the broader community. So when I work on problems, I'm thinking about health, safety, and those areas that really drive the types of applications that I've worked on and that I talked about today.
All right. Thank you, David. A popular question we have here that comes with some congratulations also is, what is the most important factor that has provided you with support in your career?
So what is the most important factor that has provided me with support? So I've had support from my family, and that has been tremendous. As I said, my mother, she told me yesterday that she told my dad, who passed away, that I won this award. He would have been so proud. But I also want to thank this community. I mentioned my mentors, and I still think of myself as a curious youngster who goes to these mentors, many of which are sitting out here in the audience, and it's being able to engage with such a tremendous set of people that I'm just humbled by, and also the likes of Dr. Sidney Fernbach, who the award is named for. I really give a lot of credit to Dr. Fernbach for really motivating us to think in this way, to be problem solvers. Thank you.
Great. Thank you, David. Let's thank both of our Davids for excellent talks this morning.
Thank you.